Good afternoon to everybody. We are now on week 3 of Happy Fun Quarantine Time, and I'm choosing to call it week 3 because the first week didn't really count, and if I add numbers, it just gets more depressing. So this afternoon, I'm going to be teaching on something I've never taught on before. Last year I skipped it just because we didn't quite have time to squeeze it in, and I figured it was not a big deal, but it's really kind of a fascinating thing, and there's lots of fun stuff we can do with it. We're going to be talking about electric fields and charges. And I'm going to start us off by asking a trivia question. The question is, according to Mr. King, when is physics the best physics it can possibly be? And I'm going to spoil it for you and tell you the answer. The answer is when it behaves like chemistry. Because basically what we're going to be doing is we're going to be taking a concept from way back in chemistry, first semester, and we're going to be expanding on it and adding a little bit of math to it. So we're going to be talking about electric charges. Some of this stuff is going to be stuff you already know. I'm hoping most of it is stuff you already know. We're going to go ahead and jump on in here. Electric charges, you should already know a little bit about this. You've got both positive and negative electric charges. Whenever you've got charges that are similar to each other, I have two positive charges and bring them close together, they will tend to repel and push each other away. However, if I have opposite charges, a positive charge and a negative charge, they tend to attract each other. And so there's a force between any two given electric charges. It can be a repulsive force or it can be an attractive force. We can quantify these little positive and negative charges, and this is where some of the chemistry comes in. The little positive charges are, of course, called protons. If you have a particle that's uncharged, it's called a neutron, and then a negatively charged particle, of course, is an electron. Okay, all of that is super basic chemistry stuff. We measure electric charge, especially in the quantities we're going to be looking at, in a unit called a Coulomb. Charge is measured in coulombs. The smallest possible electric charge you can have is the charge on a single electron, and the charge of a single electron is 1.6 times 10 to the negative 19 coulombs. We're talking very, very, very small charge. That may not ring any bells for you just yet, but take a look at this next slide. Way back in Chemistry 1, when we were talking about different experiments that led to our understanding of the parts of an atom, one of those experiments was Millikan's oil drop experiment. So if you take a look at the slide here, the way that this worked is they had a chamber where they shot in a very fine mist of oil drops. Now, those oil drops were allowed to fall through a pinhole one at a time and then viewed through a microscope. Now, they also had charged plates sitting above and below that were radiating off an electric field. And so these little oil drops had two forces acting on them. They had gravity, which was pulling them downward, and they had an electric field, which was pulling them upward. And so they were able to balance those forces out, and as a result, those oil droplets would levitate in midair. And when they were holding perfectly still and not moving, they were able to measure the charge that they were applying. And the charge that they applied was always some kind of multiple of that 1.6 times 10 to the negative 19 coulombs. So that's how they figured out the charge on an electron. Okay, and that's all ancient history. A little bit of basic stuff. You already know what a conductor and an insulator is. Conductors allow electric charges to move freely through them. Insulators don't. So that you know. However, you can transfer electric charges between conductors and insulators, and you can do it a couple of different ways. If you touch them together, then that is what is called a contact charge. Okay? You get this whenever you scuff your feet on the carpet and you reach up behind somebody and zap them in the back of the neck and give them a shock. You are transferring that electric charge to them by touching them, or when you scuff across the carpet and you touch the doorknob and you shock yourself. That's a contact charge. However, you can also charge a conductor by means of something called induction. Now, this is super relevant to modern technology, and more specifically to everybody's favorite modern technology, cell phones. We're going to talk about induction and inductive charges. Induction is a way that you can transfer a charge from one object to another one without actually touching them. Now, I'm going to show you in the slide coming up here. Whoop, go back. If I bring a charged object close to an insulator, then what happens is that the charges that are already present in that insulator align themselves with that charged object, okay? And so it causes what's called an induced charge or an inductive charge. Wireless cell phone chargers work this way. You can put if you got like one of those little Qi wireless charging pads and your phone lets you do this, you can just set your phone on this pad, and without having to actually plug anything in, electric induction from the pad itself causes charge to build up in the battery of your cell phone. Now I'm going to try and do something. I'm going to try and swap over and bring up the camera because there's a really cool thing. I'm going to show you a thing here. This is a thing. Minimize some windows to make it easier to see. This is a thing called an electroscope. Now, what you see right here is you've got a little metal ball attached to a shaft, goes down into a chamber, and in that chamber I've got two little metal leaves, two little pieces of foil just kind of hanging there. I'm going to turn the brightness down on my computer so that it's not reflecting on the glass. It might be a little bit easier to see that way. Let me turn that dude off. Okay. You should be able to see those two little metal leaves inside there. Now what I'm going to do, I'm going to angle my camera down where you can see what's going on inside of the chamber here. I've got a little piece of rabbit fur. Don't ask where it came from. Okay, I'm just kidding. It came from a rabbit. And what I'm going to do is I'm going to take this rabbit fur and I'm going to rub it on this plastic ruler. And as I'm rubbing it on this plastic ruler, what's happening is it is transferring some electric charge to this ruler. It's also really kind of nasty. Now I'm going to bring the ruler close to the ball at the top, and I want you to watch what happens to the leaves inside there. Oh, you see it? So I bring it close, they start moving. Now that's inductive charge. What's happening is that I'm bringing the charges that are on this insulated ruler close to the conductor, and it's causing those charges to line up. Now if I touch it, I want you to notice that they stay spread out. And in fact, I can even rub on the ruler a little bit more, get a few more electrons built up on this, bring it closer, and they get even further and further apart. Now, there's an electric repellent force going on in between those two electrodes in there. As soon as I touch the ball at the top, then it's going to ground out, and all that charge is going to rush up into my hand, and watch what happens. Now they're hanging back down like they were before. So that's inductive charge. Now the important takeaway from this, let me see if I can put everything back like it was here. Okay. Long and short story of it is that an electric charge will give off what's called an electric field. And that electric field, you don't actually have to be in physical contact with the charge in order to experience it. It is something that radiates outward from the point of that charge, and it diminishes the further away that it gets. And turns out that there are some interesting bits of math that you can do with that. So now we're going to talk a little bit about something called Coulomb's law. Okay, you already know that a Coulomb is a unit of electric charge. Turns out that Coulomb's law and electric charges are a lot like gravitational fields. If you remember way back talking about gravitational attraction between two objects, you would take the mass of one object and the mass of another object and multiply them together, but then you would divide by the square of the distance in between them to measure how much gravitational force was going on. Coulomb's law, it turns out, is just like that. Here is Coulomb's law. Coulomb's law says that you can measure electric force between any 2 points. We're going to call the charge of the first one Q1, the charge of the second one Q2. You multiply those charges together, divide by the distance between them squared, and then you multiply the entire thing right there by something called Coulomb's constant, and that gives you the electric force between the two of them. Coulomb's constant is not something that shows up in your slideshow for some reason, which I think is kind of silly. So I'm going to swap over to my webcam real quick. I'm going to do a quick zoom in on this. Coulomb's constant is this thing that I've got here in the middle, and that's worth writing down somewhere. It's actually 8.99 times 10 to the 9th, and then the unit is Newton meters squared per Coulomb squared. But for our purposes, just keep the math simple, we're just going to call it 9 times 10 to the 9th. Okay, so all that you do is you drop this in for Kc. Kc is Coulomb's constant. And that's how you can calculate the electric force between any two charges. We'll come back to that and we'll work some examples here in a few minutes. Now, I'm doing you and myself a favor. There's an awful lot more math that gets into this, where you can actually like plot out kind of a map of electric charges, and then you can calculate and then use vectors and sine, cosine, tangent to actually map out directions of electric forces. I'm not worried about doing that. I'm really more worried about us covering this, making sure we get it, and then moving on to DC circuits hopefully next week, which is a lot more fun, a lot more practical application. So this talks a little bit about vectors, but don't worry, I'm not going to make you do any kind of vectors. Coulomb force or electric force is a field force, meaning that it radiates from a certain point, like I'd already mentioned, and it can be between any two objects. So even though the two objects don't have to be in direct physical contact, there is still a force radiating in between them. You can also have electric fields coming from a single charge, kind of like what you saw with the ruler there. And so you can calculate electric field strength from a single charge in a lot of the same way that you do when you're using Coulomb's law to calculate the field strength between two charges. In fact, it's almost exactly the same formula. If you look here, the only difference between this and what we saw a minute ago, this is calculating electric field strength for a single charge. So instead of going charge 1 times charge 2, all you're doing is taking that charge divided by the distance from the charge that you're measuring squared, again, times Coulomb's constant. So same kind of math, easy peasy. If you have a charged object and there's an electric field around it. I've given you a PhET lab this week, which I'm going to talk about some more in the morning, that lets you actually measure and verify and then map out electric fields. And I played around with it quite a bit when I was putting the lab together. It's hopefully going to be a lot of fun to experiment with. But when you get to that tomorrow, this slide right here is something that is going to apply to the lab. Positive charges, again, those are protons. They're symbolized as positive Q or a small red dot. Negative charges are negative Q electrons. Electric fields, because they have both direction and magnitude, they are vectors. And so electric field vectors will be symbolized as arrows. And the length of the arrow corresponds to how strong those electric fields are. The longer the arrow is, the larger the electric field force is. Don't need to worry about this. Don't need to worry about that. And if I'm not mistaken, that takes us to the end of the slides, because there's not just an awful lot of slides to this. What I wanted to do is I wanted to look at some of the practice problems that go along with what I've been talking about here. And if you're joining us late in the game, then I'll have all this up on video for you to watch later. But for right now, I'd like to come back out to the webcam. I've got the two formulas we're going to be using. This is formula for looking at the electric force between two charges. This is looking at field strength for a single charge measured at a certain distance. And then, of course, there's Coulomb's constant. So we'll keep those handy. Let me take a look here. Let's take a look at question number 1 under additional practice on the practice problems here. Okay, the safe limit for beryllium in air is 2 times -6 grams per cubic meter, making beryllium one of the most toxic elements. I don't think that that's really anything important to our problem, but let's keep on looking. Charge on all electrons in the beryllium contained in 1 cubic meter of air at the safe level is about 0.085 coulombs. Now that does seem like it's going to be useful. Suppose this charge is placed 2 kilometers from a second charge. So calculate the value of the second charge if the magnitude of the electric force between the two charges is 8.64 times 10 to the -8 newtons. All right, so let me get some scratch paper out for that. Okay, so we've got, what we're looking for is we're looking for a second charge. So we know that Q1, that's going to be the charge of one of our electrons. That's going to be 0.085 coulombs. Okay. We're going to be looking for Q2. We know that our distance is going to be 2 kilometers. Now, I believe that this is going to need to be in terms of meters. So I'm going to go ahead and change our distance, which is our R, to 2,000 meters. And so we're going to be using this formula right here. We know that our electric field force, F elec, is equal to 8.64 times 10 to the -8 newtons. I know you can't see that. Just getting it all transferred down here. So if we're trying to solve for Q2, and then of course our Coulomb's constant is 9 times 10 to the 9th, what I'm going to do is I'm going to try and rewrite this formula. You know, again, like always, you have the option of plugging numbers in and then solving for whatever's unknown algebraically, or you can algebra your equation to get the variable by itself, and I'm going to do that. So starting off with our main thing right here, if I'm trying to get Q2 by itself, then I'm going to need to divide both sides by Kc, multiply both sides by r squared, and divide by Q1. Okay? And if that's a little bit too fast, I'll try and take those one at a time. We've got electric force equals Kc times Q1, Q2 over r squared. So I'm going to divide both sides by Kc. So that's going to put Kc down here, get rid of Kc over here. Multiply both sides by r squared. Just going to get rid of r squared on this side. and then divide both sides by Q1. Just going to get rid of Q1 here. So it's basically going to be R squared times electric force divided by Coulomb's constant divided by Q1. So when I plug all that in, it's going to be 2,000 squared times 8.64 times 10 to the negative 8th divided by 9 times 10 to the 9th, and our Q1, which we said was 0.085 coulombs. So now that I have all my numbers, I'm going to plug those into the calculator and see if it gives me anything that makes sense. Calculator on. Okay, so I'm going to go 2,000 squared times 8.64 times 10 to the negative 8th. Now remember, you've got to be really, really careful to make sure your calculator knows that what you want it to do is really what you're telling it to do. So be sure you're using your exponent key, or be sure you're using lots and lots of parentheses. Divided by 9 times 10 to the 9th, and then divided by 0.085. When I mash enter, it gives me a charge of 4.5 times 10 to the negative 10th coulombs. Say 4.52 times 10 to the negative 10 coulombs. I know you can't see that. And that would be my answer. Okay, number 9 says that by 2005, in the distant future, the world's tallest building will be the International Finance Center in Taipei, Republic of China. Okay, suppose a 1 Coulomb charge is placed at both the base and the top of the International Finance Center. The magnitude of the electric force stretching the building is 4.48 times 10 to the 4th newtons. How tall is the International Finance Center? Great question. So let me get some paper handy for that. And hold it where we can still see our constants here. There we go. Flawless. Okay, so let's identify the variables that they give us here. This time we're looking for distance, so we're going to be looking for r. Okay, we don't know what r is. It says that a 1 Coulomb charge is placed at both the base and the top. So we're going to say that Q1 equals 1, Q2 also equals 1, and it says that our force of electric, there are ants invading my office. Why are there ants invading my office? What's that about? Come here, you. See, look. I have an ant. I don't have an ant anymore. Oh, the horror. Okay. It says that the electric force between the two is 4.48 times 10 to the 4th newtons, so 4.48 times 10 to the 4th. And we need to find r. So I'm going to be using Coulomb's law, this formula here on the left. This time I'm solving for r. So what we're going to need to do is we're going to need to rewrite that formula to get r by itself. So I'm going to do a little bit of gymnastics here. Actually, no, that's not going to be that hard. Let's start off by rewriting our formula. Electric force equals Coulomb's constant times Q1, Q2 over r squared. Okay, so since right now everything's being divided by r squared, I'm going to get r squared into the numerator by multiplying both sides by r squared. Just going to cancel it on this side. And then I want to get r squared by itself over here, so I'm going to divide both sides by my electric field force. Cancels it off this side. And then to get the square out, I'm going to take the square root of both sides. So in other words, R is going to equal the square root of Coulomb's constant times Q1 times Q2 divided by my electric force. Let me get that back up where you can see it. There we go. So let's plug in some numbers here. It means it's going to be the square root of 9 times 10 to the 9th times 1 divided by 4.48 times 10 to the 4th. So let's calculator that. I'm going to save my square root for the very end just so I don't complicate things too much. I'm going to go ahead and just work everything that's on the inside. So I'm going to go 9 times 10 to the 9th divided by 4.48 times 10 to the 4th. Gives me this number. I need to take the square root of this, so I'm going to hit square root of my answer. Looks like the tower is 448 meters tall. Okay, so I'm going to say that R equals 448.21 meters. And it's really just that easy. Big thing is figuring out variables that are in the problem itself and trying to solve for them. I will be happy to work one more for you if somebody will shout me out a suggestion. Excellent suggestion, Brenley. Let's take a look at number 4. Okay. Wow, that's so crooked. Okay. In 1990, a French team flew a kite that was 1,034 meters long. That's a really long kite. Imagine two charges, positive 2, I'm not sure what an NC is, if that's like a microcoulomb, negative 2.8 microcoulombs at opposite ends of the kite. Calculate the magnitude of the electric force between them. If the separation of charges is doubled, what absolute value of equal and opposite charges would exert the same electric force? Why did you have to pick out a mean one? That's mean. But okay, we'll take a crack at it. Give me just a minute, and I'm going to figure out what the heck a NC is, because I don't like that. Okay. Let's see what Google says. Okay, it's a nanoCoulomb. I did not know that. A nanoCoulomb is 1 times 10 to the 9th coulombs. Okay. Now we know. So let's come into our, pull our thing back up here. Okay. I'm going to jot that down. That seems important. Okay, 1 nanocoulomb equals 1 times 10 to the 9th big coulombs. Wait, is it 10 to the 9th, 10 to the negative 9th? I just said 1 times 10 to the 9th. Okay. Fair enough. Okay, so let's look at, looks like we're going to be doing two charges. One's going to be positive this time, and one's going to be negative this time. Now that means that the force between them is going to be an attractive force. So first of all, it wants us to calculate the electric force between. So we're going to be calculating F elec. So F elec. Good news is we're not going to have to move our formula around for this one. is equal to Coulomb's constant times, I'm going to go positive 2 times 10 to the 9th, and I'm going to go negative 2.8 times 10 to the 9th. Okay. Over, now this time it's 1,034 meters, so I'm going to go 1,034 squared in our denominator. You'll shout at me if any of that looks wrong, but I think that's right. And then remembering that Coulomb's constant is 9 times 10 to the 9th. So let's pull up the calculator. Wow, glare. Okay. So I'm going to say 9 times 10 to the 9th times, open parentheses, 2 times 10 to the 9th times negative 2.8 times 10 to the 9th divided by 1,034 squared. Whoop, that's wrong. 1,034 squared. Close parentheses. Tells me the electric force between them is negative 4.71 times 10 to the 22nd. Force, I think force is newtons. So negative 4.71 times 10 to the 22nd newtons. So F-elec equals 4.71 times 10 to the 22nd. That's a lot of newtons. Okay, now let's read the second part of that problem. If the separation of charges is doubled, what absolute value of equal and opposite charges would exert the same electric force? That seems like it's just kind of playing a mind game question with us, but so let's think on this. If we were to double our force down here, right? I'm sorry, double our distance. So we're doubling our distance that we're currently squaring. It wants to know absolute value of equal and opposite charges would exert the same electric force. Okay. No, I get what they're saying. So this is going to be our new electric force. So they're tricking us into doing another problem here. But this time, what they want us to do is they want to say that that is equal to Coulomb's constant times, now they're wanting, they say equal opposite charges? Yeah, equal opposite charges. So we're going to be taking whatever Q is times negative Q divided by, now this time instead of 1034 squared, it's going to be 2068 squared because we're doubling the distance. So I'm going to go ahead and combine these up on top here. Negative Q times Q is going to be negative Q squared. Everybody okay with that? So what I want to do is I want to solve for negative Q squared. So I'm going to be doing a little bit of playing around with this number right here. I'm going to, in order to try and trim this away, I'm going to divide this number by Coulomb's constant. I'm going to multiply this number times 2068 squared, and then I'm going to take the square root, and I'm going to see what that gives me. Okay. Now I know taking the square root of a negative is a losing game, but I have a feeling that once we get closer to it, it's not going to be that big a deal. So I'm going to start with the number we had before my calculator gets bored and goes to sleep. I'm going to divide it by Coulomb's constant. So divided by 9 times 10 to the 9th. Okay. I'm going to multiply it times this right here. So times 2068 squared. Uh-oh. I broke a thing. Let's see what I broke. Oh. I hit divided by because I'm an idiot. So times 2068 squared. There we go. So that tells me that q squared right here, or negative q squared is equal to that. So if I was to change this to a positive, 2.24 times 10 to the 19th, so how do I do that? Let me go negative answer. There we go. Now let's take the square root of this answer, square root of our answer. Oh, it gives me a nice big number that's not easy for me to write down. So I'm going to go ahead and change it into scientific notation. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4.73 times 10 to the 9th. So I'm going to have 4.73 times 10 to the 9th and negative 4.73 times 10 to the 9th coulombs. Or I could just do, I guess, like 4.73 nanocoulombs and negative 4.73 nanocoulombs, because that's what that means, right? So there you go. That's number 4. Again, nothing too terribly complicated, but it's just playing around with variables and plugging stuff in, doing a little bit of algebra, and solving for what you need. Okay, so I'm going to go ahead and end the recording here. I'm going to stick around for the next 13 minutes, though, so if anyone else has any questions either about this or about anything else physics related, last week, the stuff that was due yesterday or this week or anything else, I'll be happy to try and answer that for you. Everybody else, good luck and do the best.